Hi guys, welcome to the video on metallic solids. This video is continuing on with the series all about different types of solids and their properties. Metallic solids can be found in section 12.3 in your textbook. So metallic solids, which are simply called metals, consist entirely of metal atoms. So silver, gold, zinc, right? That consists of only metal atoms. And these are metallic solids. These are metals. The metallic solids have cores that consist of a sea of electrons. So you have the metal ion, which is the nucleus plus the core electrons, and then you have these valence electrons that simply move about the structure. And within these solids, the attraction is stronger than intermolecular forces, but it's not strong enough to be covalently bonded. So there must be some special type of bonding that exists. And this is actually metallic bonding. So metallic bonding happens because the valence electrons are delocalized throughout the entire solid. So what that means is the electrons are spread throughout the solid rather than associated with a specific atom. So when it comes to metallic bonding, you could think of a metal simply as a group of cations that are suspended in a sea of electrons. This electron sea model shows these metal cations in this sea of valence electrons. The electrons are confined to the metal because of the electrostatic attractions, and they're uniformly distributed throughout. However, the electrons are mobile, so they can move all around the solid, and no individual electron is confined to any particular metal ion. So this electron is not attracted only to this corner ion. It can also move and come to this ion, or it could move back up into the right-hand corner. So these electrons can move throughout the solid. Thermal conductivity, ductility, malleability, this is all explained by this model. So thermal conductivity is the ability to conduct heat. And this is explained because the movement of electrons actually allows the transfer of kinetic energy throughout the solid. So this is why metals are such good conductors of heat. You're able to bend them and you're able to draw them into thin wires. So when you think about metals, there's probably a few key properties that you think of. The first one is that metals have a characteristic cold feeling when you touch them. This is due to their high thermal conductivity. Metals are able to conduct heat very well, which is why typically we use pots and pans that are made of metal. Silver and copper actually possess the highest thermal conductivity than any other metal. Other properties are the high electrical conductivity. So metals are very good conductors of electricity. And the reason being is because the electrons flow very easily throughout the solid. Easier electrons can flow throughout the solid or even throughout a solution, the more likely it is to conduct electricity. Most metals are also malleable, which means they can be hammered into thin sheets. And then they're also ductile, which means that they can be drawn into long, thin wires. And that's because when you bend a metal or you draw it into a wire, this doesn't change the environment around the metal core. It simply moves the electrons around. So all of these properties exist because atoms are capable of slipping past one another, where ionic and covalent solids don't exhibit this behavior. They're brittle. So the metallic solids are able to bend and slide past one another simply because of the sea of delocalized electrons. So one unique property or unique application of metallic solids are alloys. So alloys are simply mixtures of metals. So they're materials that contain more than one element, but they have characteristic properties of metals. Alloys are really useful because it's one way to modify a pure metallic element. For example, almost all of the uses of iron involve alloys. So an example is stainless steel, right? Stainless steel is mostly iron, but it's been injected with some other elements which allows it to resist corrosion. Another example is pure gold. If you actually get pure gold, it is extremely malleable. You can actually put it into a thin sheet, you can draw it into a wire. It's very, very soft. Because gold is used in a lot of jewelry, they needed to somehow make the gold harder. And what they actually do is they use alloys of gold in order to increase the hardness. Usually alloys will still conduct electricity because typically they inject more metal in it rather than non-metal. And sometimes only the surface of the solid actually changes. So an example is sometimes you see oxide layer on stainless steel. Sometimes that's the only difference. So alloys can be divided into 4 categories. So we're going to look at substitutional alloys, we're going to look at interstitial alloys, heterogeneous alloys, and then intermetallic compounds. So the first type of alloy that we're going to look at are the interstitial alloys. The interstitial and substitutional alloys, so both of these are homogeneous compounds, so they're homogeneous mixtures, which is also called a solid solution. And what that means is the components are dispersed randomly but uniformly. So again, substitutional and interstitial alloys are homogeneous mixtures. In an interstitial alloy, it forms between atoms of different sizes. So typically you have to have an atom that is significantly smaller, because in an interstitial alloy, a second element actually fills in a space or a hole in the lattice of the metal atom. So no original metal atoms are being removed, but you can see down here that we have solid iron. And what happens is you can actually put much smaller carbon atoms into the holes to create this interstitial alloy, which is steel. So the reason that interstitial alloys are so important is because it actually makes the lattice more rigid, which actually will decrease malleability and ductility. So again, this is steel when you have carbon in the spaces between the iron atoms. So in order for this to form, we have to have a solute that has a much smaller bonding radius because it has to fit in the hole. So in this case, the solute is what we are putting in, which is the carbon. The solvent, I know it's weird to think, but the solvent is actually the iron atoms. And typically with interstitial alloys, just like this steel here, we have non-metal elements that are being fitted into these holes. The reason we put these nonmetals in is because now we can actually have covalent bonds formed between the iron and the carbon. Because we have these covalent bonds forming, this causes the metal to be harder and stronger. So then with a substitutional alloy, like I said on the last slide, this is also a homogeneous mixture. So again, this is a solid solution. In this case, a second element actually takes the place of the original metal. So one atom substitutes another in the lattice. In a substitutional alloy, we have 2 metallic components. They have to have similar atomic radii and bonding characteristics. So with the substitutional alloy, you're going to substitute one metal element or one metal atom in for another. So for example, silver and gold, they could actually substitute one for another. And this is actually how we get 14 karat gold. So we actually remove some of the gold atoms and we replace it with silver, which notice it has a similar radius. And then this allows the gold to become harder. And this is how we can actually use gold in jewelry. So another example is brass. If you substitute some copper atoms with zinc, we can actually get brass. The next type of alloy we have are the heterogeneous alloys. So unlike substitutional and interstitial, heterogeneous alloys are heterogeneous mixtures. So they are not uniformly distributed. Typically it can contain 2 phases. So this doesn't necessarily mean solid, liquid, gas. What this actually can mean is we have iron metal and then we also have an iron compound. So in terms of the 2 phases, we simply have metal and a compound, and these are mixed to create this heterogeneous alloy. And so the properties can actually depend on the composition and how the solid is formed. So the manner in which it is formed can also be dependent on the properties. So then the last type of alloy actually isn't a mixture at all. Instead, it's what's called an intermetallic compound. So an intermetallic compound, as you could guess, is a compound not a mixture. Because they are compounds, they actually have definite properties and their composition cannot be varied. Right? So it has definite properties, definite composition, but the different types of atoms are ordered rather than randomly distributed. So unlike the other types of alloys, which are mixtures, the intermetallic compounds have specific order to them. And the order of the atoms generally leads to better stability. So it's more stable in terms of the structure, which also gives it higher melting points than what you might observe in the individual metals. These are actually very useful for high temperature applications, but typically they're brittle. So even though they're very useful when it comes to high temperature, these intermetallic compounds can actually be quite brittle. But some of these examples, so this nickel and aluminum intermetallic compound is actually a major component in jet engines simply because of its strength at high temperatures and its low density. So it's actually a pretty low density compound, which is useful when you want to put a really heavy engine on an airplane to fly in the air. This Nb and Sn and the tin compound is actually a superconductor. So it can actually conduct electricity, little to no resistance, which is also pretty useful.